So this is scientific literacy and misinformation, as I mentioned before. And we're essentially going to be covering the parts of a scientific paper and uh, scientific misinformation, ways to kind of recognize it, ways to avoid being gotten by it. So number one is the parts of the scientific paper is the abstract. Abstracts are a summary of paper's findings and a great way to figure out what it's about. Abstracts are listed at the very top of papers and should be the first thing that you read after the title. It's a good idea to read through the abstract before you jump into the results or data. It will give you kind of a Spark Notes version of the entire paper and let you know if it's one you want to read and really dig into. And papers can be really long, so you don't want to get halfway through or even all the way through and realize it's not about the topic you're researching and that you wasted 3 hours of your life that you're never getting back. It really sucks. So make sure to read that and just realize what it's about before you dive through an entire paper. Abstracts will have an introduction to the field and study topic, summary of the methodology and findings, and a summary of the conclusions and meaning of the study. Introduction. So introduction explains the purpose of the study and why it's important. It will contain background information necessary to understand the study. This is going to be more specific than the abstract. Abstract is going to be very general. It's written for scientists who aren't necessarily in the field the study is focusing on, but it's more for general population. And the introduction is going to be kind of in between. So this and later parts in the study. So it's going to be more specific than the abstract, but less specific than other parts of the study that are later. It ends with the research question, which is what the study aims to answer. It can be helpful to read, especially if you're not super familiar with the field. So like I said, it gives kind of background information on the field and specifically this study and what kind of the information necessary for that study is. Then you have materials and methods. So this is the really dense part. This is written for scientists active in the field of study. It uses really specific terminology and can be very dense. And it should be detailed enough for someone else to recreate the experiment from only that paper. So it'll have specific chemical reactions used. It'll have specific models of equipment used. It'll have the settings the equipment was used with. It'll have temperatures used, times. It'll have pretty much everything you need to recreate the experiment, and you should get the same result as that. It discusses how data was collected and analyzed. It can include specific kinds of measurements taken, but like I said before, corrections made to data to account for known errors. So that can be if, say, you have you're collecting data about locations of fish in the ocean. If you know that there's some error where you messed up taking samples, or you know that you didn't move as far as you maybe should have away from each sample site, so there's a good chance you tagged the same fish twice. That can be in there. It can be other things, just anything that you think might have messed up your data can be included there. And also more specifically what statistical methods you used to correct that data. And also what equipment was used. So be patient with yourself when you're reading this. Google is your best friend. If there's something you don't know, if there's a word you don't know, which is most likely going to be the case, because again, this is written for a very specific audience. This is scientists who are doing research in this field. There's a very low likelihood that you're going to know all the words and all the terms that are used in it. So if you're reading it and there's like, I don't know what that word means, just Google it. It'll make it a lot easier. Then there's the results. So this summarizes all the data gathered and analysis performed. This has no interpretation. So this is not going to be, well, we think this means, this is not going to be, well, this is why we think this happened. This is just going to be, this is what we saw. This is how we gathered it. This is what we saw. It will not explain the meaning or suspected cause of findings, just the actual observations. And it will contain the likelihood of results being random chance or there being a pattern. This is what's known as p-values or probability values. So that's going to be essentially in any data set, you're going to have random variations. And so there's something called the chi-square test, which essentially allows you to calculate a probability that a specific result came from just random fluctuations in data or came from an actual cause that caused a specific pattern. And so that's going to be the p-values. It's going to contain most of the figures and graphs in the study because this is where the data analysis happens. So it's going to have most of the graphs and charts and stuff. Much of the data analysis, although figures and numbers might be referenced in other sections. So you might have in the discussion, which is the next section, or the abstract in the beginning, it might reference a number as like, we found that this number of fish species was in this area. But this is where the actual data analysis and how they got that number is going to be contained. In the discussion, so this is the interpretation of the results. So this will have the researcher's opinion. It's not just going to be, this is what the data is. It will be through the lens of their specific study as well. So it will be answering their hypothesis and their questions. So it will be, our data shows XYZ, and that supports or rejects our specific hypothesis. It will include why researchers think the patterns that were seen, why they think they exist, and what might have caused them. And it will most likely include references to older pieces of research and other known effects. So sometimes you might see, especially in this section, references to studies that were in like 1970 or 1964 or something. The reason is because those are what are called foundational literature. So that's kind of papers that are so integral to a field that everything else, everything more recent, is kind of built off that. And so pretty much all studies in a specific field that has foundational literature is going to be referencing that, just because it's so important to future analysis after that. So that's why you might see studies that cite stuff from like 1970 or something. Like, why is that in there? That's why. And then it will contain how this study impacts others in the field. So it may discuss errors in the study. And it will include reasons the study is relevant and important in the field. And then conclusion. So this is not in all papers, but it's going to be essentially a mirrored version of the abstract. So it's a short summary of the paper with the simplified findings. Again, it's not going to be in all papers, but when they do have it, it's usually going to be right after the discussion, and this is going to be pretty short. So, suggested reading order. What I just told you is the order, how it's going to appear in papers. It's going to go 1 through 6 in that order, top to bottom. But this is the suggested reading order. So you don't have to read every paper all the way through. You will spend every waking moment reading papers if you do this. Don't do this. This is the order I suggest reading papers in to make it as manageable as possible. And this is also an order I got from some teachers who are involved in research. So it's not just me saying what I think is best. It's a good order. You can read it from top to bottom, but you'll have to slog through the materials and methods before getting to the discussion. And the materials and methods is really dense, as I said before, and a lot of times it's not really important unless you're trying to replicate the study or doing peer review on the study. It's much more important for most people to look at the discussion. So the title and abstract, number 1, what you want to read, and it'll let you know if you need to keep reading. You don't need to read past this if it's not applicable. And then introduction, discussion and conclusion, materials and methods, and then results. So if you read all the way through, you can go back and read it top to bottom. That's really not necessary unless you're doing a report on the study or something. If you're just reading it because you want to learn about it, you don't need to go back and read it again. Um, Again, don't read more than you have to. Papers are long. They can be confusingly written and annoying to read. So just take it easy with the reading. So we're going to do a little misinformation activity. This is kind of dividing line between the parts of a study portion and the misinformation portion. So in the chat, if you want to do a time, or can you think of a time when you encountered scientific misinformation that you knew was false or inaccurate?
It says the chat is disabled.
What? Why? Okay, hold on.
I don't know if that's happening for anyone else, but that's for me.
It is.
Yeah, same here.
Okay. Does everyone have a mic? You can just like talk about it, I guess. That works.
Yeah, that's fine. Before I deleted Instagram, there was so much misinformation that I totally fell for too during the beginning of the pandemic. And it was overwhelming, but I'm glad that I deleted all of that.
Yeah, it's really prevalent on social media sites, definitely. Anyone else?
I read a lot of studies, and something that I've noticed, like kind of a trend that I kind of find deceptive, is when studies will use relative risk instead of absolute risk to represent their data. And I don't know, it just bothers me because I know that the absolute risk is supposed to apply to the population, but relative risk only applies to the study pool. So I don't know, that's just something I notice a lot.
Yeah, I mean, I think definitely it should include both, but I think they do relative risk just because a lot of studies are really specific in their target groups. Like if a cure isn't meant for like the wider population, if it's just for this specific group, it doesn't really matter if it has a ton of effects on the wider population. But I definitely agree it should have more absolute risk values. Can you think of a time when you didn't check a source to see if something was true?
It happens too often, honestly. I've gotten better at it though. Like I usually, like if I repost something like really quickly that I see on social media before like verifying it, I've gotten into a habit of just quickly going and verifying it so I don't look like a dummy.
Me
Yeah.
too.
Big stuff.
Yeah, definitely. And then what are some dangers of articles or social media posts that don't accurately portray scientific advances or misrepresent scientific consensus on an issue?
I guess just I guess just the spread of misinformation in general is, I mean, I don't know. For me, like I feel like I try to validate or verify as much as possible, but I know that a lot of people don't. And so it's very easy for people to be convinced of stories that seem very convincing or persuasive, but that really don't have any scientific, like anything valid, no data to back it up or support it. So I feel like it happens a lot. But I usually just ignore it, or I might make a comment and be like, this is wrong.
Yeah. Yeah, at least one thing that comes to mind for me is especially with kind of the more dangerous, like conspiracy theory minded ones, it seems a lot more persuasive because it's coming from someone you know, and you don't want to think, people you know would lie to you. You want to think they're right. So a lot of times people will believe stuff more if it comes from people they know, say from social media, rather than just from a random newspaper that they don't know anyone at. So that's kind of an aspect of social media that can lead to more spread. Does anyone else have any ideas for any of the questions?
No, but I literally had the same experience where I have lost a couple people for posting really dangerous misinformation on the internet that I respectfully disagreed with them on, but they just couldn't agree to disagree, and it was really difficult.
Yeah, yeah. It gets very emotional. It can be not fun. All right. So scientific misinformation. How does it start? So even the wildest stories usually aren't completely fabricated. Are there some things that are completely fabricated? Yes. Even something like anti-vaccine beliefs did not come out of nowhere, though. There was an incredibly and horrendously flawed paper in the 90s that claimed there was a link between the MMR vaccine, which is measles, mumps, and rubella, and autism. And there's absolutely no link, just to be clear. The person who authored the study had their medical license revoked. Uh, incredibly, incredibly shady. Lots of financial issues and conflicts of interest. But that's not what got press. What got press is just asking questions about the MMR vaccine, and it caused a lot of parents to question the medical establishment. Um, and this later got expanded to all vaccines causing autism, and eventually dozens of other effects besides just autism. And while there are side effects to vaccines, it's always worth the minuscule risk unless someone is in a very rare group. For example, has an autoimmune disorder. But all it takes is one person to do a bad experiment, and the results can get even further distorted from there. It takes excellent science communication at all levels, from studies to articles to social media posts to people mentioning results to each other, even like in conversation. If even one of those steps oversimplifies or clickbaits or doesn't understand the work, it can cascade really quickly. Yes, Jay.
Um, I just wanted to make a comment about because I see this a lot, and I've actually been vaccine injured. And a very frustrating thing for me is when people tell me that it's not possible that I was vaccine injured. Like it wasn't possible that I almost died, that like I had this awful experience. So I think that with this, I think it's a very sensitive and very controversial subject in general. But there are people that are injured that didn't have, any health issues prior, like any other, like I've been vaccinated against everything else. But I had a vaccine reaction to the flu vaccine and Gardasil vaccine. And yeah, it's really hurtful when you have people that like don't agree, like don't believe you. I've even had doctors that don't believe me, and I'm like how like do you like I like that I don't know. I just want to say that it goes both ways. Like there are people that do get injured, and a lot of the times it's very frustrating for them, and they end up going to social media or something just to be heard because they get shut down by doctors a lot of the time.
Yeah, I'm just talking about MMR right now. Um, I'm not saying that there's no side effects, that there's no way anyone can have an effect from anything. I'm just talking about MMR uh, and autism and those effects, and a lot of the claims that came from that study, which had no evidence and no basis. Um, yeah, I'm sorry to
Sorry,
hear that.
kind of jumped in on there. Sorry, didn't mean
No
to.
problem. No problem. I'm sorry to hear that. All right. So, how does misinformation spread? So, studies can be picked up by clickbait sites, for example, tabloids, and some social media users and bloggers. Um, And then the inaccurate or misrepresented findings can then reach the general public, where further distortion can occur as it is shared from person to person. Um, this can be worse if the study was funded by a group with misinformation in mind, as they will often fund its spread through ads or getting publications to talk about it. So examples could be climate change hoax studies funded by fossil fuel companies, health and nutrition studies funded by like soda companies or snack companies, transportation studies funded by car manufacturers, other examples. And many companies will use the public's trust in kind of science as a concept to influence beliefs in ways that will increase corporate profits. And then who gains from misinformation? So pretty much the only people who don't gain from scientific misinformation are the people who believe it. It allows the sale of products or services that have no actual merit, but causes people to have a reason to buy them anyway. It's really easy to invent a magical cure all if it doesn't actually need to cure anything. You just have to be good at marketing. It allows the growth of a conspiratorial mindset in people. So people who believe the Earth is really flat and a shadowy cabal is keeping people from realizing it are much easier to convince of other conspiracy theories, like global warming being a hoax. And that can have benefits for example, fossil fuel companies. And then the potentially lucrative expert career shilling for fake products. So some experts, and I'm using the term expert loosely here, make whole careers from finding a new cure for cancer or something. It's often much easier, faster, cheaper, and better in every way than the existing product. But the reason you haven't heard of it is that the blank industry is trying to protect their profits, so they won't let this new method get out. Now, this has happened before. For example, car manufacturers spent decades trying to kill electric cars and bills that would fund non-car infrastructure. But that doesn't mean that it's happening in whatever industry someone is claiming to have revolutionized. So I'm not saying that that doesn't happen, but just because someone says my magic cure is being repressed by this industry doesn't mean it's actually happening. So experts, someone having a PhD or MD next to their name doesn't necessarily mean anything. What field or specialty is the degree in? Example, a chiropractor doesn't have any special authority when discussing global warming or something. Same thing with like a doctor doesn't have any authority really discussing theoretical physics. So try and find the consensus of the field you're looking at. No issue will have complete agreement by everyone. There are usually theories that will be more respected and widely accepted than others. If most researchers seem to be divided on a topic, it's a good indication that more work needs to be done and super definitive conclusions probably shouldn't be drawn. Look at previous work done by experts and try and find out what peers in their field think of them. If someone has very few published studies and is not well known in the field, but suddenly came up with this solution to a massive problem overnight, it might be a good idea to wait for some peer review to happen before completely believing it. Not to say that people can't come out of nowhere and have incredibly prolific scientific careers, but it's just something to be aware of and monitor. Look for funding or retainers given to experts. Unfortunately, some scientists are complete shills and are paid large amounts of money to produce inaccurate research for corporations or other interest groups. That way, the companies can point to a study and not technically be lying when they make an outrageous claim. Remember that this is only a tiny, tiny minority of scientists and researchers, but it only takes a few to create misinformation that can then be boosted and reach large numbers of people. And so this is opensecrets.org. It's more for politicians than scientists, but you can find websites like that and look up, does this person on the board for nutrition and dietetics, does this person have a retainer from Coca-Cola? That might be a mark against their credibility. Techniques. Ask who gains from findings and changes in public perceptions. For example, again, fossil fuel companies benefit if people believe a study that minimizes the effects of climate change. Look at sources. Try and find the original publication of a finding. If you can't, that's a fair indication that the source you found initially might not be too reliable, as they aren't citing their own sources. If you kind of find a website that links to another website that links to another website that links to another website that doesn't link anything, you don't really have a credible citation in the first one. It's just linking to nothing. It needs to actually link back to an actual study that is credible. Don't just read headlines. I know this is really hard. I do it way too much as well. But it's really important because that's where people clickbait. They put the most controversial, eye-catching aspects there, and if you just read that, then you're not getting the full story. So pay attention to how new studies are portrayed. Look out for findings that are extremely decisive. So this is absolutely the solution to this problem. There's no other way that these results could be interpreted. Not usually how studies work. There's always possible error in a study. It's never really 100% is correct. Kind of studies that portray like an underdog narrative or going against the establishment or completely overthrow a field's current understanding. I'm not saying this means the finding is wrong, but it is a sign to not take the information at face value because it is a tactic it can be a tactic to kind of allow people to believe them and set up as I'm doing this great research, but big science is not letting it get out. Incredible studies should state possible sources of error and will most likely not act as if their finding is 100% correct and no other interpretation of their data is accurate. Don't be overwhelmed. So a lot of scientific misinformation is banking on people not knowing how to check sources or being overwhelmed by reading a study. I know this is a lot of effort and time to put in. Most of the time you won't have to go through all these, but the more you do it, the easier it gets. You also don't have to research every aspect of every claim you come across. You would lose your mind if you tried to do that. So prioritize the subjects you're interested in, and if a claim might get you to change behavior, also try and research those. So now that we know a bit more about scientific misinformation, we can do the activity again if you want. Any of the questions? Anyone have any more examples?
None that I can think of.
Okay. So that's pretty much it. Got my little works cited here. Bio 21, Professor Meyer. So that's a class I'm currently taking. I used a lot of her slides for the parts of a scientific paper, and my science 10 teacher, Professor Santos. He also been using a lot of his information. And this is just mostly here to remind you it's important to cite your sources. Yeah.